Today we're going to look at the Doppler effect, sometimes called the Doppler shift. This is the phenomenon where the frequency of a wave changes when the source of the wave or the observer of the wave is in motion. An example of the Doppler effect from everyday life is when a vehicle passes you at fairly high speed. For example, if an emergency vehicle has its siren going, when the vehicle is coming towards you, the frequency of the sound will sound higher pitched, and when the vehicle is going away from you, the frequency will sound lower pitched. In this lesson, we're going to try and use physics to explain why this phenomenon occurs. As an example, let's use an ambulance. Now suppose the ambulance is driving down the road, it's got its siren going, and there's a pedestrian in front of the ambulance listening to the sound waves. Now I can't say for certain where the ambulance's siren is actually located. It might be up on top of the ambulance along with the lights, or it might be under the hood or in the front of the ambulance. Let's just say, for the sake of argument, that this ambulance, its siren is located right under the front of the hood. So I'm going to position the ambulance with the siren located right at the origin that I've drawn on my coordinate system here. So the siren is producing oscillations of the air molecules, and those oscillating molecules bump into neighboring molecules, causing them to oscillate as well, and that's essentially what sound waves are. Now the animation that you're looking at right now, this isn't actually what sound waves look like. The animation is illustrating a transverse wave. And hopefully you recall from the previous lesson, transverse wave means that the direction of the oscillations are perpendicular to the direction that the wave's traveling. So the wave traveling towards our pedestrian here is moving from left to right, but the oscillations in the illustration are up and down. So the animation that you're looking at is a transverse wave. Sound is actually a longitudinal wave. A longitudinal wave, in the case of sound, involves air molecules which are oscillating parallel to the direction of motion of the wave. So the air molecules are oscillating left to right, not up and down. If we could see the individual air molecules, it would look something like this. We would see rarefactions. Rarefactions are regions with low density. There's very few molecules there. And halfway between rarefactions, we would see compressions. Compressions are areas of high density where there are a lot of molecules. So why have I got an animation of a transverse wave to illustrate sound waves which are actually longitudinal? Well, it's primarily because transverse waves are easier to visualize and to graph than are the longitudinal waves. Let me just pause the wave for an instant. Think of this animated wave as illustrating not the motion of the air molecules, but the density or the pressure of the air. The rarefactions, because the molecules are far apart, the rarefactions correspond to low density and therefore low air pressure. So that would correspond to a low point on the graph. The compressions, on the other hand, have a high density or a high pressure, and so the compressions would correspond to the high points on the graph. Sound waves are sometimes referred to as air pressure waves, and the animation, which looks like a transverse wave, is actually a graph of the air pressure as the sound wave passes. Now you notice that the amplitude of the wave is getting smaller as the wave moves away from the ambulance. The reason for this is because the sound wave isn't just traveling in one dimension, it's traveling in 3 dimensions. So as it moves away from the ambulance, it's spreading out over a larger area. And because the same amount of energy is spread out over a larger area, that's what causes the amplitude to get smaller. And as a result, the farther away you are from the ambulance, the less loud the siren is going to sound. If the pedestrian wasn't directly in front of the ambulance, if I move the pedestrian off to an angle here, there would be waves traveling in this direction as well, towards the pedestrian. Same thing, if I move the pedestrian off to the side of the ambulance, there would be waves traveling there as well. So the animation that we've got here is only showing the wave in one direction. In fact, the wave is spreading out in 3 dimensions. Now, it would be very confusing if I tried to draw all of the compressions and rarefactions as a wave in 3 dimensions. So what we're going to do instead is we're just going to draw what are called the wave fronts. Allow these wave fronts to spread out, and then I'll pause them. There we go. So what these blue circles represent are the compressions spreading out from the source, which is at the origin, where the ambulance's siren is located. There's a compression right here, 1 wavelength in front of the ambulance, and then there's another compression, 2 wavelengths and 3 wavelengths and 4 wavelengths in front of the ambulance. That's going to be true in all directions. So 1 wavelength from the source in this direction, and 2 wavelengths and 3 wavelengths and so on All these blue points forming the circles, those represent points that are compressions. Now this pattern of wave fronts might remind you of ripples spreading out, for example, when you drop a stone into a pond, and that's exactly what they are. When you drop a stone into the pond, you're creating waves, and those ripples, those circular ripples, are the wave fronts produced by that wave. Now we're talking about the Doppler effect, so what we want to look at is what effect does the motion of the ambulance or the observer have on the frequency of the waves. So before we get to that, let's just measure out and mark off the wavelength of this wave. And this is with the ambulance not moving. So we've got a stationary ambulance producing waves, and we've measured off the wavelength and we've recorded it here for future reference. Let me move the observer back so that he is directly in front of the ambulance. And let's restart the animation. And what you can see is that the wave fronts continue to spread out in a circular pattern. The waves will pass by the observer, and the observer is going to hear the waves as the compressions and rarefactions pass his location. What I'm going to do now is run the animation again, but this time let's have the ambulance moving. Let's set the speed of the ambulance to about 1/4 of the speed of the waves, and let's see how that changes the pattern of wave fronts. Okay, let me pause the animation. What you can see is that we still have the circular wave fronts being created, but the circles are no longer centered on the origin. The largest wave front actually is still centered on the origin because that's where the ambulance started. Once the ambulance starts moving, the rest of the wave fronts are going to be centered on the ambulance's location when that compression was produced. So the second wave front is shifted a little bit to the right due to the fact that the ambulance is moving to the right. And then the next wavefront after that is shifted a little bit more to the right. If we turn the animation back on, you can see that the wavefronts are moving to the right along with the ambulance. Now what this means for our observer is when the waves arrive at his location, they're no longer the same wavelength apart that they were when the ambulance was stationary. Because the ambulance is moving at 1/4 of the speed of the waves, what that means is each of these wave fronts is shifted 1/4 of a wavelength to the right. And that means when our observer measures the distance between those wave fronts, he's going to find that the wavelength is only 3/4 or 0.75 of what the wavelength was when the ambulance was stationary. So in front of the ambulance, the wavelength is reduced by 1/4 because of the fact that the ambulance is moving at 1/4 the speed of the wave. If the observer was standing behind the ambulance, we would find that the wavelength as measured by that observer is now 1/4 of a wavelength longer than it was when the ambulance was stationary due to the fact that the wavefronts are shifting 1/4 wavelength in the opposite direction from the observer. Let's run the animation again, giving the ambulance a much higher speed. Let's have the ambulance moving at 0.9 of the wave speed. What you can see now is that in front of the ambulance, the wavefronts are really close together, and behind the ambulance, the wavefronts are really far apart. Because the ambulance is traveling at 0.9 of the speed of the waves, each compression in front of the ambulance is only going to be 0.1 of the original wavelength behind the compression in front of it. So in front of the ambulance, the observed wavelength is only going to be 0.1 of the original wavelength, whereas behind the ambulance, the wavelength that's observed will be 1.9. It will be much larger than the original wavelength. Now let's see if we can come up with an equation that describes the Doppler shift. If we start by referring to our datasheet and go to the waves section, the first equation is the equation from our last lesson, which tells us that the speed of the wave is equal to the wavelength divided by the period. We can rearrange that by multiplying both sides by the period. That will isolate the wavelength. So the wavelength should equal the speed of the wave multiplied by the period. Now this equation does not account for the motion of the source. As our animation shows, if the source of the waves is in motion, the observer in front of the source will see that the wavelength is reduced based on how fast the source is moving. Now here's the equation that's been modified to account for the motion of the source. So lambda, that was the original wavelength when the source is not in motion. Lambda with a subscript O That's the observed wavelength. That's what our observer sees or hears when he is standing in front of the source. As we showed with the animation, the original wavelength, which is v times t, is going to be reduced by the distance that the ambulance moves in one period. So distance is still speed times time. The difference here is that we want to use the speed of the ambulance, which I've labeled Vs, S for source, rather than the speed of the wave, which is just v. So based on this equation, if the speed of the source is 1/4 or 0.25 of the speed of the waves, that's going to reduce the observed wavelength by 1/4, so it will be 3/4 of the original wavelength. If the speed of the source is 0.9 of the speed of the wave, that's going to reduce the wavelength to 0.1, as we saw in the animation. Now, since the period t is the same in both terms, we can factor that out, and we can write the observed wavelength as the difference between the wave speed and the speed of the source multiplied by the period. So we've looked at the effect that the motion of the source has on the wavelength, but it's possible that the observer might be in motion as well. Let's reset the animation. We'll put the observer back in front of the ambulance. We'll set the ambulance speed back to 0, and we'll run the animation again. And now, because the ambulance is again stationary, the waves are now evenly separated. They're all back to their original wavelength. Now, if our observer was walking away from the ambulance, his motion isn't going to affect the distance between the compressions. It's not going to change the wavelength. However, it will affect the period. If the observer is moving away from the waves, it's going to take longer for the compressions to catch up to him. Let me give the observer a ridiculous speed like 0.9 of the speed of the waves. Once one of the compressions reaches the observer, it's going to take a very long time for the next compression to reach him, due to the fact that he's moving at almost the same speed of the wave. So the period that the observer hears is going to be much longer than the actual period of the siren. On the other hand, if the observer is moving towards the source at a very high speed, he's going to cross those wave fronts very, very quickly. The time between compressions is going to be very, very short. So we want our equation to be able to account for the motion of the observer as well as that of the source. So let's have a look at the next equation. TO, that's the period between the waves, or the time between the compressions as measured by the observer. To calculate that, we're going to take the distance between the waves, which is lambda O, and we're going to divide by the speed of the waves. However, if the observer is moving, the relevant speed is the difference between the wave speed and the observer's speed. As we just demonstrated with the example, if the observer is moving at close to the speed of the wave, say 0.9 of the wave speed, then the difference between v and VO is going to be very, very small. And when we divide by that small speed, we're going to get a very long period. If the observer is moving towards the source, that would mean that the VO is negative, and since we're subtracting a negative number, we're actually adding. We're going to get a larger denominator, which means our period is going to be shortened. So we proposed two separate equations. The first equation that we wrote shows how the motion of the source affects the observed wavelength of the waves. The second equation shows how the observer's motion affects the observed period of the waves. What we want to do now is we want to combine the two equations into one. So we're going to take our first equation for lambda O, which is this expression here. We're going to substitute that in to the second equation. So we're going to replace the lambda O in the second equation by this expression here. And that tells us that the period of the waves, as observed by the observer, is given by this expression. So we've got V minus Vs in the numerator multiplied by the actual period of the waves divided by V minus VO. Now the formula is often expressed in terms of frequency rather than period. Remember that frequency is the reciprocal of the period. So to take the reciprocal, we're going to switch the numerator and the denominator. So the V minus VO, that's going to move up to the numerator. The V minus Vs moves down to the denominator. The t, if we leave it as a t, we'd have to move it to the denominator. However, the reciprocal of t is the frequency, so we can just leave it where it is if we change it to the frequency. So in this formula, Fs represents the actual frequency of the source. Fo, that represents the frequency that the observer hears. The v is the speed of the waves. The Vo and the Vs, those are the speeds of the observer and the source respectively. Now there are a couple of limitations of this formula. First of all, this is just a 1D formula. If the observer and the source were moving at an angle towards each other and not in a straight line, the formula would be more complicated. So we're only going to use this formula for 1D situations. The other problem, according to Einstein and his theory of relativity, time starts to do weird things at very, very high speeds. And so we have to make a relativistic adjustment to the equation. This is the non-relativistic form of the equation. So this is good for sound waves or for waves on the surface of a pond, but it's not good for light waves. Light waves travel so fast that we need to use the relativistic formula if we want to calculate the Doppler effect for light and other forms of electromagnetic waves like radio waves or X-rays and so on. There are a number of useful applications of the Doppler effect. For example, the Doppler effect is used in traffic enforcement to measure how fast vehicles are moving. A radar gun is used to send radio waves towards the vehicle. When the waves reflect off the vehicle, they'll have a higher frequency due to the Doppler effect when the vehicle is approaching the radar gun and a lower frequency when the vehicle is moving away from the gun. The radar gun can measure the frequency of the reflected waves and can then determine how fast the vehicle is moving. Doppler effect is also used for aviation. Here's a photograph of the radar installation at an air traffic control tower. The radar sends radio waves out into the sky. Those radio waves will reflect off of any nearby aircraft, and the reflected waves will allow us to determine where the aircraft are, and due to the Doppler effect, we'll be able to tell how fast they're moving and whether they're moving towards or away from the airport. Doppler radar is also used in meteorology to track the movement of storm systems. In astronomy, the Doppler effect is used to determine whether astronomical objects are moving towards or away from the Earth. When an object is moving towards the Earth, the light coming from the object will have a higher frequency when we observe it from Earth. We say that the light is blue shifted because the highest frequencies of visible light are towards the blue and purple end of the visible spectrum. When the object is moving away from Earth, it will be red shifted. What that means is that the frequency will be lower than normal due to the Doppler effect. You may have heard it said that the universe is expanding. Astrophysicists believe that this is the case due to Doppler effect measurements. It turns out that distant galaxies exhibit a redshift, indicating that they're moving away from the Earth. And the farther away the galaxy is located, the faster it's moving away. Let's look at an example where we can use the Doppler effect formula to solve a word problem. An ambulance moves at 20 meters per second with its siren producing sound at 1200 hertz. Calculate the frequency that a stationary observer will hear in front of and behind the ambulance. So we'll start by writing down the Doppler effect equation that we derived earlier. And then if we look at our illustration, we've got the ambulance moving with the velocity of 20.0 meters per second. That's Vs, that's the velocity of the source. The sound waves themselves are originating from the ambulance. They're traveling towards the observer who's in front of the ambulance. So that's the vector v, that's the speed of the sound waves. The observer is stationary, so the speed of the observer is going to be 0. So in this formula, because VO is 0, we can just cross it out and ignore it, and we can get a somewhat simplified formula without the VO. Now the V in the formula is the speed of the sound waves. We can get out our data sheet. The speed of the sound waves is listed under the constants. So the speed of sound in air, it depends to some degree on the air pressure and the air temperature. Under standard conditions, sound waves in air have a speed of 343 meters per second. So when we're doing the calculations, we'll use that standard speed of sound as our V. So if we substitute the values into the equation, we're going to use 343 in both places for the speed of the waves. We're going to use 20.0 for the speed of the source, and we're going to use 1200 hertz, the frequency of the source given in the question. So we'll type this expression into our calculator. 343 divided by 343 minus 20.0 and then times by 1200. And the calculator tells us that the observed frequency is 1274 hertz. Or if we round to 3 significant digits, 1.27 kilohertz. So this is the frequency or the pitch that the observer actually hears. If we compare that to the actual frequency of the ambulance siren, which was 1200 hertz, we can see that the observer hears a higher frequency as a result of the Doppler effect compared to the actual frequency. Okay, now let's switch the ambulance and the observer around so that the observer is behind the ambulance. So the ambulance is still moving to the right, the ambulance is still going forward. The observer is behind the ambulance. So what that means is that the sound waves are now traveling in the opposite direction. If the observer is on the left, the ambulance is on the right, the waves have to travel from the ambulance to the observer. So that's now in the negative direction. So to do the calculation behind the ambulance, we're going to use exactly the same numbers. The only exception is that the 343, we're going to make that negative because it's now in the opposite direction. So we'll type this expression in on our calculator just like before. We'll type in negative 343 divided by negative 343 minus 20.0 times 1200. And we can see now the observed frequency is going to be 1134 hertz. So as expected, when the observer is behind the ambulance and the ambulance is moving away from the observer hears a lower frequency than the actual frequency of the ambulance. Let's look at a second example. As I ride my bike through the park, I hear a 720 hertz sound ahead of me. I realize the sound is a bird singing. When I stop to listen more closely, I hear the sound at 710 hertz. How fast was I riding? Let's start by making an illustration of the scenario. We've got the bird, which is the source of the sound, and we've got the bike rider, which is going to be the observer, the person hearing the sound. The sound is traveling from the source, from the bird, to the observer, the cyclist. In this example, it's the observer who's moving. It's the bike that's moving, it's not the bird that's moving. So it would be the source, which has a velocity of 0, and the observer is moving, the way I've drawn it, the observer is moving to the right, so that would be the positive direction. Now the equation is exactly the same for the Doppler effect as it was in the previous example. What's different is that this time it's the source that has a velocity of 0, not the observer. So we're going to cross out the Vs, and if we simplify the formula, it's going to look a little bit different than last time. We're going to have to do some algebra this time. The frequency of the source is the frequency that I hear when I'm not moving, so that's the 710 hertz. When I am moving, I hear a higher frequency of 720 hertz, so that's the FO, that's the observed frequency. The V is the speed of the sound waves, that's going to be 343 meters per second. The way I've drawn it, with the observer to the left and the source to the right, we're going to have to make that 343 negative because that's the direction the sound is traveling in. And that leaves us with VO as the unknown. So to do the algebra, we want to get the VO by itself. I'm going to first have to multiply by V, and that'll move the V from the denominator of the right over to the left. And at the same time, if I want, I can divide by Fs. I need the Fs and the V both to move over to the left side of the equation. Once I've done that, I've just got V minus VO remaining on the right side. Since we're trying to get the VO by itself, we need to get rid of the V next. We need to move the V from the right side to the left side. So we're going to have to subtract that from both sides of the equation. So if I minus V from both sides, I will be left with negative VO on the right side of the equation, and I'll have this expression here on the left side of the equation. The last thing I need to do is to get rid of that negative sign, which means I can multiply all of the terms in the equation by -1, and that just reverses all of the signs. So VO is going to equal negative V times FO over Fs plus V. Now we can replace the symbols by the measurements. The V in both places will replace the V by negative 343 meters per second. The FO, the observed frequency, is 720 hertz. The actual frequency of the source is 710 hertz. Now in the first term, I've got a negative sign, and I've got a second negative sign with the 343. Those two negative signs are going to cancel, so I can ignore both of those negative signs. So typing this expression in on the calculator, I get my answer. VO, the speed of the observer, the speed of the bike, is 4.83 meters per second.